Well, thanks for the chance to be here. Appreciate the invitation and input from the co-authors listed here. I guess the task for this talk was to go over issues related focused on water. You know, too much and too little water represent serious problems. We've heard about that a lot this morning, from the impacts of flooding on the energy side of things to human health, to issues of drought and agriculture. And I was surprised to see the talk this morning about how the request for insurance money was most for agriculture on flood-related problems. I was surprised by that. So as you can see from the co-author list here, there's contributions from a number of people. I'll be highlighting some of those along the way. And I'll organize this around water supply, and then in terms of the flood and extreme precipitation problem, and then a few thoughts on adaptation ideas. First of all, from Dan Cahan and company was years ago already major finding about the potential impact of climate change on snowpack. And this is an update to that from Dan. And what this figure in the bottom shows is, if you look at the, let me get the pointer here. There you go. If you look at the region in the upper right here, this is the colored in areas are the regions of snowpack. And you look at a time series over 150 years and how much the average snowpack is in the Sierra. The gray dots are the observed in the 50-year period from 1950 to 2000, and the red and blue dots are an ensemble of model simulations and projections. The curves represent the mean, and then the 90th percentile and the 10th percentile. And the message is really clear from this. Things are going down when it comes to snowpack in the Sierra as the climate gets warmer. And there's a lot of interesting findings regarding that that help us put that in perspective. Essentially, the median by 2050 drops to 2/3 of the historical median. So we're down by 33% in terms of snowpack at that time. And if you go out to 2100, we're down 2/3 from where we have been historically the last 50 years. Now, I should emphasize something here, and that is that the variability from year to year is very great in the snowpack in the Sierra Nevada. Year-to-year variations, and the extreme values are a factor of 10 apart from one another. So this is a long-term trend on top of a large interannual variability. This is another illustration of that problem. And you can see with the 1961 to 1990 scenario, moving out to the middle of the century with two different versions of warming, and what this would look like spatially. I mean, this is a profound change in terms of water supply for the state of California. And this is crucial, as I'm sure most of you know, because essentially that snowpack is like a giant natural reservoir that gives the water much of the state needs throughout the dry season. So how the fate of this reservoir, so to speak, will determine a lot about how we deal with or how much water is available in the dry season. And another statistic that's rather startling is that by 2100, the chance of achieving what we're used to today as a median value will only be 10%. 90% chance of less than what we have on average today. And a growth from where we are now to a 40% chance of being below today's 10%. So basically drought will become more prevalent when it comes to snowpack. I'll shift gears here to another serious problem we heard about earlier today, and that is the delta and the change in the subsidence associated with the land in the delta here. You can see a nice schematic that shows the different processes involved. And you know, with the levees, it's possible and has been possible to keep up with that to a large degree. But as a couple of speakers pointed out earlier today, this is an area of significant vulnerability. As the sea level rise continues, and no one's mentioned the problem of potential ice sheet melting, I think is a big wild card out there. You know, the prospect of the delta being inundated is very real. And this has a huge impact potentially on water transfers, which are crucial for water supply in much of the southern half of the state. So this is a fundamental infrastructure vulnerability. Many people are aware of this. I just thought it important to highlight. Turning now to another major source of water for the state is the Colorado River. And there's been a lot of different studies over the last decade or so on what the Southwest climate's going to look like, and dry and hot. And I'll never forget Mike Dettinger's remarks at a California climate change conference. Summing up his talk was the West is worst and first when it comes to climate change. And I think the Colorado River Basin is emblematic of that. But there's been large variations in the projections of how much of an impact there will be in runoff for the Colorado River. The current runoff over the last 30 years has averaged about 15 million acre feet. The current allocations are 16.5 million acre feet. There's a fundamental problem there. And the projections of how that's going to change in the future are obviously very important. So there's been a study conducted, and this was through the Western Water Assessment Regional Integrated Science Assessment Program in NOAA and the University of Colorado, in collaboration with other RESAs, as we call them, elsewhere, to try to pin down what is that range of uncertainty and see if it can be reduced a bit. So this graph highlights different scenarios. These are, how much carbon dioxide is in the atmosphere, basically, and the range is shown here as is the range of projected changes based on that scenario using different models from different groups. And this was in the Colorado Climate Report and a publication there. And the punchline here is that the temperature, basically it's going up. It's hard to deny that. The range of precipitation uncertainty is pretty large, and the range of runoff is large as well. But the punchline here is that a decrease of somewhere between 6 and 20% is what the group came up with as a projected change in runoff for the Colorado River Basin. 10% would be about 1.5 million acre feet per year. That's how much water is supposed to go to Mexico. I don't know how much that compares to what goes to the area east of here that has such a vital agricultural role. So how representative is that result? A more recent update even is from a meeting with that broad collaborative team from several RESAs that got together to try to brainstorm what is going on and how to resolve this. And this report is from about a year ago. And the punchline here is that we see about -5 to -10% range in this one study. And these points here illustrate why there's a range. Basically, the devil's in the details. How much water is consumed in the soil by plant growth is very tough to measure and to represent that over a whole water basin. Another thing is how snow is evaporated in wind, how runoff gets from the snowpack into the groundwater, and how that gets into the stream. These are very complicated processes. There's a lot of parameterizations involved, so there's inherently a fair bit of uncertainty. And one of the things that really stuck with me on this subject is that one of the biggest changes for the Colorado Basin is in the demand. And in this case, the folks who are doing this work refer to demand as the natural system. Think of plants consuming water that is not then going to get into the streams and be part of the runoff. Imagine in a warmer climate, the growing season for that natural ecosystem expands. The chance for plants to consume more water along the way from the soil expands. They evaporate it, evapotranspire it into the atmosphere. If that's not a technical jargon, I don't know what is. Evapotranspiration. So you're going to end up with less water in the streams, partly because basically the ecosystem's consuming more of it along the way. And if you throw in agriculture and other things, I'm sure that piles on. So basically we've got a downtick on the way in the Colorado Basin, and with California dependent on Colorado River to a degree, there's an impact here on water supply. Another wildcard situation which has recently become apparent is through a project that's been sponsored largely by the California Energy Commission. We've heard Guido Franco recognized much today. I'll do the same. He came up to me in a meeting once after talking about NOAA's hydrometeorology testbed, and we launched an idea for an experiment to look at the potential of climate change impacts on precipitation events in California in more detail than we'd been able to. And this experiment took place over the last 3 winters, and we're working closely with University of California, San Diego researchers, Scripps, USGS folks, and we've had our first publication come out now. And I just want to highlight what we've found, remarkably, is that in some of the snow in the Sierra and in the rain, If you take that water and evaporate it, and then blast it with a laser, and I'm sure Jessie Creaming's here with her poster. I'm butchering the explanation of this, but you blast those little dust particles that remain and you can figure out their chemistry, and it becomes a fingerprinting process about where that material came from. And some of it is definitively from China. Shockingly, dust from China making it over in midwinter and entering into that precipitation somehow. And what this study shows is a little bit of how that happened. If you look up here, what you see in the brown is the dust source region in China. Think of the big deserts out there, and they're phenomenal satellite pictures of this. I mean, you can see it with your own eye. It's incredible. But some of that actually makes it across the Pacific and ended up over the Sierras in February and March of, or at least in March of 2009. And this graph is time in this direction, and this is vertical. So at this little point right here, we had a NOAA radar pointing upward, looking at the precipitation aloft, telling us where it was. And that's what the green represents here. So it started off with deep cloud, then the cloud went away a bit, and then we had these turrets of cloud poking up into about 4 or 5 kilometers altitude. And at the bottom here, imagine someone collecting samples of water and then seeing the Asian dust in it. That's the smoking gun. And with this radar data, we were able to see how high the clouds were, but we weren't sure that that was the right layer that we would expect the dust to have come across the Pacific in. It could have been higher up, and the clouds never would have gotten there, or lower down, and they would have rained elsewhere. But what this brown area represents is the time and height region where what's called a back trajectory model showed that air parcels coming out of the dusty region here made it all the way across the Pacific and ended up over our observing site in the Sierra Nevada, and out of that came this rain and snow. To me, the most remarkable part of this is that we studied 2 storms, and that with the same methodology, sampling-wise, and the first storm had no Asian dust, and the second storm was dominated by Asian dust or related aerosol particles. And you heard about atmospheric rivers earlier today, and I'll tell you quite a bit more here in a few minutes. But we looked at the 2 storms, and I've been looking at atmospheric rivers for several years now. I have never seen 2 ARs, as we call them, look more similar. And when we calculated the amount of water vapor transport that those ARs were producing, they were within 2% of one another, of being exactly the same amount of water vapor transported during the storm period. But and we know that that transport is the most important factor in determining how much rain or snow forms in the coastal mountains or the Sierras. And yet, these 2 storms, the second one had 40% more precipitation in it. We saw dust, the remnants of it in the precipitation in the Sierra. We see that the layers where the clouds penetrated to made sense that air came from Asia. So now we're doing more work in the last 2 years. We've continued to work on this, and we've sampled a lot more cases, and we've actually flown an aircraft now, a research aircraft with the Department of Energy up here, and sampled, and guess what we found up there was Asian dust in the tops of these clouds, changing it from liquid water to ice, and there's a whole series of things that then happen to increase the precipitation efficiency. So this is a formal publication in Journal of Geophysical Research. The results I just mentioned from this year are still not published yet, but as an experimentalist, the beauty is you see the data firsthand, and usually you know the results often right away. So this is a fascinating process. We think it may have a significant impact on California precipitation amount. And in case you're wondering, yes, climate change could impact the amount of dust that comes out of Asia. So very interrelated, complex problems. Exciting problem we've been working on scientifically, very important practically. All right, now having touched on water supply primarily, and by the way, this could actually play a role in extreme precipitation events as well, taking what was already going to be a fairly strong storm and boosting it just even a bit more. And then in addition, and I'll put I'm a weather guy. I'll put the meteorologist, hydrometeorologist, whatever you want to call it. When we predict precipitation, right now the numerical weather models that do that, they don't have dust in them. And yet we're seeing evidence of a potentially important impact. So this is a major direction I think we'll be seeing work on for several years to come. And I have to say thank you to the Energy Commission for helping get this rolling. Thanks to NOAA folks for participating, and for Scripps and other partners as well. All right, let me turn now to the other side of the equation, that is the extreme precipitation and flooding. And if you can't figure out where this picture's from, This is a river coming out of the coast north of the Bay Area. This is the Russian River hitting the coast during the big El Nino of 1998. Heavy precipitation, flooding are very significant problems in this region, and this is a study that showed the analysis for the nation. And the punchline here is California, on average, $370 million a year of flood damages over this 17-year period, and third highest in the nation. Why is that happening? Well, we have a lot of big storms, and this is a result hot off the presses in the Bulletin of American Meteorological Society. Mike Dettinger and myself, we came up with a scaling for precipitation over 3 days of basically 8 to 12 inches, 12 to 16 inches, 16 to 20 inches, or greater than 20 inches in 3 days. And if you plot on, there's 6,000 data points around the country, the maximum type storm that they ever experienced, and we call these rainfall categories, or RCATs. You can see the reds are the biggest ones, and you might imagine the hurricane problem or the big thunderstorm problem, that's where these come from. But look at California and the West Coast. These happen to be comparable to what happens elsewhere in the country. So one of the reasons California has such serious flood damage is we have as serious a rainfall problem as any other place in the country. Well, what gives rise to those, I'll talk about in just a moment. This is a graph from Mike Anderson, California Department of Water Resources, over 100 years, looking at some indications of extreme event behavior in terms of runoff. And here we have the American River shown in light blue and the Feather River shown in dark blue. And the punchline is, if you look at these numbers up here, before 1950, you have these values for the maximum 3-day flow, the average, and the minimum. And after 1950, look how much these have changed. Big changes in both the going up on the average and the max and down on the minimum. And you see the same sort of behavior on the Feather River. So in this fairly large geographic region of Northern California, we're seeing basically floods that have a lot more runoff in them and dry periods that are drier than they were in the first half of the century. One of the things we've come to expect from climate change projections is that it's the extreme events that are more likely to change. This is courtesy of Mike Dettinger, and what you see here basically are curves of observed frequency of occurrence of extreme precipitation, and here's what the projections are. And by the way, the blue dots are the projections from the same model during the time period of these observations. So what this shows is the model actually handled that frequency pretty well in the period where we know what happened, and now we're using it to try to project what will happen. And this is the scenario we get. Precipitation changes mostly at the extremes. And Mike, for sake of time, I think I'm just going to highlight one thing real quick on this, and that is it's a complicated diagram, but the bottom line is this is a runoff scenario, and you look at the northern Sierra, and you see large areas of blue here, more so than here. What that means is a greater frequency of large runoff events in the northern Sierra, and you see the same sort of thing in the southern Sierra, but also you see this warmth-driven snowmelt. This is month of the year here. And you see this red stuff is the runoff in the spring creating high, this melt in the spring creating high runoff, and you see that fading a bit as time goes by. So we're seeing a change in the nature of the extreme runoff events in the Sierra. Now, one of the key phenomena we've learned about the last several years for these big events, as you saw a little bit this morning, is something we call an atmospheric river. Now, this diagram is actually a satellite image. And over the ocean, we get these kind of data that doesn't work over land. That's why they're black. So there's Japan, Hawaii, and the West Coast. And where you have orange and red is where you have large amounts of water vapor. And what this image represents is what we call an atmospheric river. Think of a region of the atmosphere. It's down in the lowest few thousand feet. The winds are fairly strong, and it's really warm and moist. And it's concentrating that water vapor transport into a relatively narrow ribbon when you think of the scale of the atmosphere. I mean, it's wide relative to a land-based river, but relative to the atmosphere, it's extremely narrow. And it turns out about 3 or 4 of these on average across the hemisphere, or in the hemisphere, do 90% of the water vapor transport in the mid-latitudes. So these are the primary phenomena that drives the water cycle in the mid-latitudes. And this is a big event from just 2 years ago that hit California. And you can see the kind of impact on the central coast, 16.5 inches of rain in 24 hours. This happened on dry soil, and in spite of that soil being dry, we saw a boost in runoff of up to almost 20,000 cubic feet per second on a river that usually doesn't have much water in it at all. And the stream flow actually jumped up 15 or 20 feet during that time as well. And this was on dry soil, thank goodness. If this had happened after the soils were moist and the system, environmental system was primed for flooding, we would have had a very serious problem. So this was published in EOS, it's called, on the cover, and summarizes a number of studies that have led to this. So from the perspective of this meeting, it's very important to look at how these might change in a future climate. This is also a result out of our CalWater experiment I mentioned, which had an aerosol and atmospheric river components to it. And Mike Dettinger published this year in Climate Change. And this image actually shows an atmospheric river in the GFDL climate model on the 18th of January, 2100. Mike will hold you to that forecast. Where are you at? Maybe I won't quite make it. But the punchline is these things are in the climate models. They're sort of fuzzy a little bit, and we're learning about just how fuzzy, but they are there. And Mike has done a very nice job of summarizing that essentially the amount of water vapor in one of these is going to be greater in the future in a number of them because the atmosphere is warmer and can hold more water. The winds might slacken off a bit. You heard a little bit about that this morning from Sasha. But in spite of that, there will still be some events where the winds are going to be just as strong as they have been lately, or historically, but the moisture will be that much greater. So there's this additional tail in the distribution of extreme events where we think there are going to be a few, for lack of a better word, supercharged ARs that will be in the mix in the coming century. Think of that as basically a flood risk problem. In addition to the fact that they could produce more water, they can provide more water, they're also warmer. And what that means is that the snow line in the mountains goes up. And what that means is you have more of the watershed exposed to rain than snow, and you increase the potential runoff in a flood. So we see these in the climate models. Now I want to turn in the last couple minutes here to a couple ideas about adaptation. I just have 3 or 4 slides here, Dan. There's a very major study the Department of Water Resources is leading on the Central Valley Flood Protection Plan. I'll highlight that in a moment. But I want to also mention the approach of developing scenarios, as they're called, whereby instead of depending on a climate model to capture all of this process, we look back historically at what's happened in the past, make some logical assumptions about how those things might come together in a future event, and how that might be changed a little bit by warmer climate and that sort of thing. And then run through the process of describing the phenomena from a scientific standpoint. In the case of what's called the arc storm, we have a flood scenario where we have very strong atmospheric rivers modeled after 2 big events that happened in 1969 in January in Southern California and 1986 in Northern California. They happened years apart, but in the 1860s, there were 2, we believe, similar events that happened just 10 days apart, which wreaked havoc for the state. And that's the basis for what's called the arc storm scenario. And in that scenario, Mike and myself and a number of other folks in our field developed the physical description of what this would look like over the course of about a 40-day period, what the rain would look like, what the winds would look like, and the like, and generated a scenario that was then run through the infrastructure system, and estimates of damages and the like were described. I'll show a slide on that in just a second. There was also a drought scenario that Jay Lund provided me. I don't have a slide for it, but it's very analogous, but it's for an extreme drought. Once again, based on historical, factual events, but in the modern era with some additional amplitude that you would expect from the information we now have on changing climate. In addition, forecast-based reservoir operations is a very big deal potentially, in the sense that today's reservoirs are operated on rule curves, they're called, that were built and developed 50 years ago, before weather forecasts, frankly, were worth making much of a decision on. Nowadays, the forecasts have gotten a lot better. There's still a lot of work to be done, and that's one of the science gaps we've identified. But the fact is, if we could envision a day where a reservoir operator could say, okay, the forecast for the next 5 days says, I'm not going to have a big event in my watershed. I'm going to keep some of that runoff in my reservoir for water supply or for fisheries or for whatever else to give me more flexibility. And I know I'm not going to add risk to flood damage because I've got enough heads up 5 days out that I can drain that reservoir down far enough that I can absorb that flood the way the reservoir was originally designed for. That's forecast-based operations. I think that's a huge adaptation strategy available if we can muster the effort and change the policies to enable it. Let me highlight just a little bit here. Dan, do I have 2 or 3 minutes? Or? Yes. Okay, I'll wrap up. This was information from Mike Anderson, basically looking at the Central Valley as a flood risk and identifying, what are the vulnerabilities in terms of people's actions and infrastructure and the economy, and then identifying what are the causal mechanisms physically for it, like the atmospheric river problem. And then assess the likelihood of exceedance. And then you have this whole process, and there's a lot of steps that go into this, but the bottom line is it's a very thoughtful process that allows us to evaluate what the risks are using a thresholding approach that's informed by information from climate projections and scenarios like we've been talking about. This is an illustration of the arc storm scenario, and the reason I wanted to show this is basically to highlight that there are places that would receive 600 millimeters of rain in a day. I mean, this has happened historically. And what happened in this storm is we basically assumed, and we know now this can happen, that storm would stall for an extra day. And it would essentially create that much more of a problem in Southern California. Similarly, the vulnerability of Sacramento has been well recognized by the national academies and many others and agencies. Huge runoff amounts up in that area as well. And the punchline being, with a full suite of economists and infrastructure specialists, it's hard to say this, but more than $500 billion of damage is what's officially projected in these peer-reviewed reports. This is Katrina on steroids kind of problem. And when the early versions of this kind of scenario were in people's minds about 10 years ago, they were too big to really grasp. And then Katrina happened, and all of a sudden the light bulb went off that, okay, we need to wake up and realize there's huge risk here beyond what we had recognized. Last point is the risks with extreme precipitation and runoff led to a request from the Western States Water Council, which supports the Western Governors Association and advises them on water issues for the Western U.S. They passed a resolution in 2011 basically asking for, recommending enhancing the monitoring and prediction capability for these extreme events in the Western U.S. And this was passed formally by a large group of people representing 17 Western states and their governors. And over the last decade or so, NOAA's hydrometeorology testbed and other efforts have really led to better understanding. I've tried to highlight this, and we've also prototyped some solutions, which I haven't been able to talk about much here. And then we developed this vision with input from 26 different experts from 20 different agencies or organizations, universities and the like, and presented it to the Western States Water Council folks in October. It was very well received. And the punchline here is that there are major strategies for better observations on land of the snow and of atmospheric rivers and of the heavy precip environments, and also better weather modeling, forecasts, and support for decision makers. And a lot of this would be enabled also by having programs for observing and monitoring conditions offshore over the Pacific. The NOAA and the nation does this for hurricanes in the summer, for the eastern U.S. As you saw in that RCAT diagram, the problems for California are comparable in the west. A reconnaissance type program focused on western storms would be a logical thing to consider. And California's actually begun the effort to implement the state network in the state to help with this through the Department of Water Resources and NOAA and Scripps. And I'll skip through these real quick and get to the punchline slide, Dan. Atmospheric rivers I want to highlight real quick, and this is a paper from Dettinger and et al. Major supplier of water for the state. About 30 to 50% of the average annual rainfall occurs in just a handful of AR events. And an individual atmospheric river can transport the equivalent of about 7 Mississippi rivers worth of water at a given moment, or in one day, 10 million acre feet of water. And about 20% of that might rain out over the state. In conclusion, California really has significant vulnerabilities to shifts in extreme precip and runoff. Risks are for water supply, snowpack, the Colorado River, and the Delta. Changes in the strength of atmospheric rivers and snow level are going to be key for future flood risks. And then improving the monitoring and prediction of these processes and looking into forecast-based operations would be useful adaptive strategies. Thank you.